Hello, teachers. I say good afternoon for everyone, and I hope that you are okay where you are. Now, as you see me, I'm a mathematics teacher. We are going to continue to learn our topic of mathematics. Again, we still review topic number 1, concerned of complex numbers. Then we are going to deal with a lesson concerned with trigonometric or a polar form of a complex numbers. Teachers, as you know, a complex number should be represented in 3 forms. The first form to represent a complex number is what we call standard form or algebraic form or Cartesian form or rectangular form. This form is what we call Z equal to A positive B at. This is what we call standard form or algebraic form or Cartesian form or rectangular form. Then, the second form as a lesson of today concerned with trigonometric or polar form of complex number. Teachers, we are going to discuss how you can express your complex numbers by using trigonometry. Then the lesson of today, lesson concerned with trigonometric form. We say trigonometric form or polar form of a complex number. Teachers, as you see me very well, we are going to discuss the second way of expressing a complex numbers. How to express complex numbers in trigonometric or in polar form. We are going, our lesson teacher here, by a supposition, by an idea or by a hint. Let point P be a point with A on x-axis and B on y-axis. Let point P with AB. This point represent a complex number Z equal to A positive BI. And I'm sure you are able, teachers, to represent this algebraic form of complex number. You are able to represent this complex number Z equal to A positive BI, represent it on a Ligand diagram. Then, how to represent this complex number on a Ligand diagram? Usually, as you know, in a Ligand diagram or a Ligand plane, it is like a XY plane, where on the x-axis you put there leopard, and on the imaginary axis you put there imaginary part. As you see, I can use a ruler by drawing. Flow, teachers, I'm going to represent my complex number Z equal to I positive BI on a Ligand diagram. A Ligand diagram or a Ligand plane, it is like a XY plane, where on x-axis I put here real part of my given complex number Z here. Real part of my given complex number Z, it is like A. And on y-axis I put there imaginary part of my given complex number Z, it is like B. Then let's suppose the measure of A. Let's suppose at this point, this is where we can localize our real party A. Imaginary part here, like a B. You put imaginary part on the y-axis. Then the point where those two parts of our given complex number should be meted on this Argand plane. That point represents your given complex numbers. I'm going to find where this part A and this part B should be meted on our Argand diagram. Look at teachers how to find the meeting point. Look at, you're given two parts, real parts and the imaginary part should be meted at this point. Then this point again becomes our given complex number z equal to a positive b I. Teachers, as you see, I represent my given complex number on a Argand diagram. Simply, in a Argand diagram, it is like XY plane, where you put your part on the x-axis and imaginary part on the y-axis. Then, after getting our complex number z here on the Argand diagram, I'm going to find the modulus of this complex number. Teachers, as you see, a modulus of complex number, it is like a magnitude, absolute value, norm, or total length of that complex number. Then, to get the modulus of this complex number, I take care this point represent my complex number. I'm going to relate my given point, represent my given complex number. I relate it with the origin of my Argand plane or Argand diagram. By doing like this one, I'm going to represent my given point related to the origin of Argand diagram, like this one. As you see, teachers, this vector formed from my given complex number z related to the origin of our Argand diagram. This vector represented the magnitude of complex number z, the same as modulus. You can use z in absolute value, or you can use small letter R to denote modulus of complex numbers. And the teachers here, as you see, there is a number formed from this modulus of complex number with the positive real part, with this real part. Angle formed from modulus to x-axis. Don't forget x-axis represents the real part of a complex number. Let's say that angle to be an angle theta. I mean, teachers, everything here is clear. Then the target of today, it concerns how to come from algebraic form or how to come from standard form of complex number to trigonometric form. Teachers, understand when you say trigonometric form of complex numbers, understand directly the presence of those trigonometric functions in complex numbers. The presence of cosine of an angle, the presence of sine of an angle in writing complex numbers. The standard form or algebraic form, z equal to a positive bi. As you see, This is a good form of complex numbers. This one is called to be standard or algebraic form. Then I'm going to find other form, how you can write this form in trigonometric form. How you can write these complex numbers by using trigonometric functions, by using cosine of an angle, by using sine of an angle. Again, teachers, return back about our Arigan diagram here. Look at again here on our Arigan diagram. Here, as you see, the small line, or like a line segment from the point Z, a line segment from the point Z, this line segment, as you see, until it reach this serial part A. As you see this line segment here, it is like a B. Here it is like a B. Again, see me clearly. The distance from the imaginary part here B until to reach our complex number Z. This distance, it is like A. Teachers, I see everything here is very, very clear for everyone. Then, as you see me, the target is how you can come from polar form of complex numbers to write complex numbers in trigonometric form. Then look at here, teachers. Are you able to find the value of this side B related to an angle theta? I mean, teachers, as you see, this is small part of line B. It is like the opposite side of an angle. Then when I say opposite side of an angle, and it is known from the concept of trigonometry, sine of an angle theta must be the same as its opposite side. The opposite side of an angle theta, there is B. B out of what? Out of hypotenuse. As I see, the hypotenuse here is what you call the magnitude or modulus of complex number. Is equal to B out of magnitude or modulus equal to R. Teachers, at this case, you can find the value of what? The value of B. As you see, B must be equal to how many? You use a cross multiplication. B must be equal to R, then times the sine of an angle theta. Then again, you can find what? The value of this side A related to our given angle theta. As you see, the side A, it is like the opposite side of your given angle theta. When I say an opposite side, you understand something. Then from trigonometric concept, we know that cosine of an angle theta, you take adjacent side here. It is like A, adjacent side out of hypotenuse. Hypotenuse, it is like a radius. As you see, that your part of complex number A is the same as a radius times the cosine of an angle theta. Teachers, see here clearly. To get a cosine of an angle, you take adjacent side of that angle out of hypotenuse. Adjacent is this part A, this small part of line A divided by hypotenuse. Hypotenuse the same as a modulus. R stand for modulus of complex number. As you see, teacher, here, my form here, I have it is what you call algebraic form. Algebraic form. And I'm able to transform or to rewrite again this real part A by using trigonometric function, by using cosine of an angle. As here A stand for x-axis, or A stand for real part. Real part of a complex number Z must be equal to R cosine of an angle theta. And it is known this angle theta is called to be argument of our complex number. I'm going to replace this real part with the corresponding value here. Real part equal to this one, and the imaginary part equal to this one. Then the complex number Z must be equal to how many? Real part, R cosine of an angle theta, then positive R sine of an angle theta as a B, but B, on B there is I. Then times here I. Then as you see here, we have a 2R common factor. I'm able to put R as a factor of those, a factor of sine and cosine. Then a complex number must be equal to R in factor of cosine of an angle theta positive I sine of that angle theta. Then, as you see here, teachers, I transform the value of real part in trigonometric form. Again, I transform the value of imaginary part in trigonometric form. Then my given complex number here, expressed in the form of algebraic or standard form, my given complex number becomes this one in the form of trigonometric form or polar form. Then don't forget the expression of complex number in trigonometric form. There is a presence of what? The presence of those trigonometric function. Sine of an angle theta and cosine of that angle theta. Don't forget again, cosine of an angle always should be located on the x-axis. X-axis is the same as the real part. And the sine of an angle always should be located on y-axis. It is like a imaginary part of that complex number Z. Then, my given complex number Z equal to A positive BI. This complex number is expressed by using standard form or by using algebraic form or by using Cartesian or rectangular form. This standard form, is it the same as R in factor of cosine of an angle theta? Cosine of an angle theta positive I sine of that angle theta. Then this form is what you call standard form. Standard or what you call algebraic form. Algebraic form. They are four related ones. Standard form, algebraic form, Cartesian form, the same as rectangular form. Then this form is equal to this one in trigonometric or polar form. When we say trigonometric, is the same as polar form. Then, teachers, I say you see me clearly. See me clearly, teachers. We have a z equal to r radius in factor of cosine of an angle theta positive I sine of an angle theta. This is a good expression of trigonometric form in complex numbers. The good expression of trigonometry in complex numbers. Simply, this is what you call trigonometric form of complex numbers. This form is what you call trigonometric. Is trigonometric is what we call trigonometric form. Trigonometric form, the same as a polar form. Polar form of complex number z, where this small capital letter R stand for the modulus. R stand for modulus. Then we say modulus or magnitude or absolute values. And this theta, this modulus, then theta here stand for what? Theta stand for what you call argument of complex number z. R stand for modulus of complex number z. Then theta stand for argument again of complex number z. As you see, r cosine theta, real part of that complex number z, equal to r cosine theta equal to a. Then r sine theta, then imaginary part of complex number z, the same as b. Generally, teachers, this is a good form of complex number expressed by using trigonometry. Expressed in trigonometric form or in polar form. Then, teacher, the question we have it is like how to come from standard form, how to come from this standard form or this algebraic form, then go to how many? Go to the form of trigonometric form. It requires teachers two things. The first thing is to find the modulus of complex numbers. I mean, everyone here is able to find a modulus for any given complex number. To find the modulus of complex number, modulus must be equal to, you take the real part square, then a positive imaginary part square, then both under square root. This is a good general form for getting modulus of complex number. And the second thing to do, you find the first one. You find the modulus. The second, how to get argument of a complex number z. Teachers, maybe there is many way of getting this argument of complex number. Me, I'm going to choose the simple one. There is many way I know for getting the modulus. Me, I'm going to use the simple one. I'm going to use this way, the simple one. Finding. We are going to discuss finding argument. Finding argument of z. Argument of z is what we call, of complex number z, is what we call theta. Teachers, a good way for finding this angle theta is this one. The first things you are able to find cosine of an angle theta and the sine of that angle theta. As you know, cosine of an angle theta equal to this one. Look at here. Cosine of an angle theta, you take a real part out of radius. Cosine of an angle theta, you take A out of radius. Then sine of an angle theta again here, you take a imaginary part out of radius equal to B out of R. As you see, I get the sine of an angle for my given complex number and the cosine of angle for again my given complex number. Then, to find this, the real value of theta here, as a teacher, as you see, the target we have is to find that the value of that angle theta. One, as you see, one should use simply, one should apply what you call trigonometric inverse law. You know that tangent of an angle, it is the ratio between sine and cosine. You can apply arc tangent to get this angle theta simply. But this way has many challenges. I'm not now. I'm not to you to find to. I'm not to apply inverse of trigonometric function or inverse of tangent to find the theta. I do it at the second time. Let's use the simple. It is like the shortcuts. Then the good positioning or the good way to find this argument, teachers, I'm sure you know some theories from trigonometric concept. You know the meaning of unit circle. As you have already discussed it together, a unit circle is a circle always centered at the origin, always the center of unit circle 0, 0 at the origin, and the radius of unit circle always must be 1. The good way and the simple way of forgetting this argument of that angle, you try to localize this angle theta on our unity circle. You try to find the position of this theta on unity circle. The first thing here, these techniques become very easy and understandable for those teachers who know the meaning of unity circle, who know to use unity circle for getting trigonometric values like a cosine of an angle and the sine of an angle. As you see, teacher, a unity circle is like a simple circle like this one. Let's suppose this simple circle to be a unity circle. Always a circle should have 4 equal parts, where each part is going to be quadrats. I'm going to divide my given unity circle into 4 equal parts like this one. Then the first part, the second, the third, and the fourth. I divide my given unity circle into 4 equal parts. I begin with that one to mention here part number 1, first quadrant. Part number 2, the second quadrant. Part number 3, the third quadrant, and part number 4, the last one of the 4th quadrant. Always the value of sine of an angle is located on the position of 1. Here, this is what you call sine of an angle theta. Then on the x-axis there is cosine of an angle theta. Then teachers, to get our argument, to get our argument of complex number. From me teachers, the simple techniques I'm going to use. Look at, I have here the value of sine of an angle theta. And I have here again the value of cosine of an angle theta. Value of cosine of an angle theta, I have it on my hand. Again, I have the value of sine of that angle theta again. From the information I have between those two things, I'm able to localize. I'm able to find where there is my given angle theta on my simple unity circle. Teachers, as you see, if the value of cosine of that angle theta, let us then to get the value of our argument here, it depends with the sign of those value. To get argument, to get where my given argument here, theta, should be located on our unity circle, depend on the sign of theta here. If then the value of argument theta, this value depends on the sign, on the signs of sine theta, depend on the sine of an angle theta and the cosine of that angle theta. As you see, the first thing here, teacher, if the cosine of an angle theta, there is that here, and the sine of that angle theta, if those two values give you positive, if the sine of cosine theta and the sine of sine theta must be both must be positive. Teachers, as you see me, I'm going to find the region where sine of an angle theta must be positive and the cosine of that angle theta must be again positive. As you see, this is part number 1, first quadrant. Part number 1. This is part number 1. The all angles located from part number 1. Part number 1 begins with 0 degrees until to 90 degrees. The angles lying between 0 degrees and 90 degrees. Those angles, the sign of that angles must be always positive and its cosine must be always positive. That shows me if I get a positive value of cosine of my angle and positive value of sine of my angle, that indicates me my given theta here, my given argument should be located in the first quadrant, because I get positive value of cosine and positive value of sine. Then if cosine of that angle must be, that cosine must be cosine negative, and sine of theta should be positive. Look at here. Positive. I want the region on my unity circle where the result from cosine must be negative and where the result from sine should be positive. Look at it is like this one. When I am here, negative side of cosine is this one. Then the positive side of sine is this one. We are here in quadrant number, the second quadrant. Here, your argument here must be located in the second quadrant from 90 degrees until to 180 degrees. If the result of cosine theta must be negative, and the result of sine theta again should be positive. Then again there is the third case. If cosine of an angle theta, that cosine of an angle theta should be positive. Cosine should be positive, and sine of an angle theta again must be negative. Look at cosine positive direction. Cosine positive direction. We are here. Then cosine positive direction, we are here. Then sine here negative direction. We are here on the fourth part, on the fourth quadrant. From 270 degrees until to 360 degrees or 0 degrees. Here your angle must be, your argument must be located on the 4 degrees. If cosine of that angle theta should be positive, and if cosine of angle theta should be positive and sine of that angle theta should be negative, then angle theta must be always localized in quadrant number 4. Then the fourth case is where cosine of an angle theta and sine of an angle theta are both are negative. Both are negative. If sine of an angle theta and cosine of that an angle theta must be positive, both means that your angle, your argument always should be located in quadrant number 3, in the third quadrant. Because in the third quadrant, it is where we are in negative values of cosine and again negative values of sine. Teachers, I mean, something is it clear for everyone? These techniques require you to know, to localize the position of your angle on unity circle. It becomes very easy and understandable. Maybe let me to deal with one example so that everything should be clear here. Then, an example. Example number 1. Transform z equal to 1 positive I in polar or trigonometric form. Teachers, see this good and simple example. We have a complex number z equal to 1 positive I. This complex number expressed in the form of standard or algebraic. Then you ask to transform this standard complex number z equal to 1 positive I in polar or trigonometric form. How to express this one in trigonometric form? Solution. Teachers, as we say before, to express a complex number in polar or trigonometric form, you must know two principal things. The first thing to do here, you find the modulus. The modulus, it is like the same as z under absolute value. The first thing you find the modulus of your given complex number. Then, modulus equal to how many? You take the real part square, positive imaginary part square, both under root. You take 1 square, positive real part again, real part 1, imaginary part again, there is 1. Positive 1 square, both under square root, you get a square root of 2. Then, after getting modulus of my given complex number, it becomes very, very simple and easy to get the value of cosine. Cosine of an angle theta, I take the real parts cosine, real part out of radius. Real part is equal to 1 out of modulus. Modulus equal to square root of 2, the same as 2 out of square root of 2 out of 2. Here you use a conjugate. Square root of 2, then out of 2. Then how to get sine of an angle theta? This value. See me clearly, teachers. To get the sine of an angle theta, you get imaginary part out of radius or modulus. Then real part equal to 1 out of modulus square root of 2. Again, this is equal to how many? You get square root of 2 again out of square root of 2. Teachers, we are together. Answer me. Then, as you see sine, cosine, as you see cosine of an angle theta equal to how many? Square root of 2, then out of 2. Then sine of that angle theta must be equal to again square root of 2, again out of 2. Teachers, as you see here, the result from cosine and the result from sine both should be positive. That shows me my given angle theta should be located in the first quadrant of my given unity circle. Because since cosine of angle theta and this sine of that angle theta both are positive. Both are positive. Positive value. Cosine of an angle theta equal to square root of 2 out of 2. Positive value. Sine of an angle theta equal to square root of 2 again out of 2. Again positive value. Because both sine and cosine has a positive sign, it shows me that argument theta should be located in the first quadrant of my given unity circle. Let's draw again a unity circle here with 4 quadrants. Look at here. Then we begin here with 0 degrees, 90 degrees, 180 degrees, 270 degrees. Again, to return back again. I ask you, because we know that the value of cosine and sine both are positive. I ask you, after getting that both sine and cosine must be positive, it means that our argument theta here should be located in first quadrant. Theta must be always from 0 to 90 degrees. Then we are going to find by using your brain. Which angle in the first quadrant, so that its cosine must be square root of 2 out of 2, and its sine again is square root of 2 out of 2. Teachers, as you remember how to get trigonometric values, especially for special angles, by using a unit circle like that one, this angle in the first quadrant with cosine is that one and sine is that one. This angle must be always equal to how many? 45 degrees. Or you can say how many? Or you can say pi out of 4 radians. Teachers, as you see me, the task we have already is over. We have this task to transform this algebraic form into trigonometric form. We must know two things. Radius is given, square root of 2, and the argument is known now. You get 45 degrees or pi out of 2. Teachers, don't forget, as a mathematician, always try to express this theta argument in radian. Use radian. Somehow to use degrees cannot be, it is not a good way for expressing. Always try to use radian when you express your argument. Then, as I know, complex numbers z equal to how many? Radius in factor of cosine of an angle, positive I sine of that angle. This is a good form of complex number z of. This is a good form of complex number z in polar form. Then where these are equal to how many? Radius equal to square root of 2, and theta equal to argument equal to how many? Pi out of 4 radiant. Then our given complex number z equal to how many? Equal to square root of 2 in factor of cosine of pi out of 4, positive I sine of pi out of 4. Here, teachers, the task here is ended. Then, as you see, the complex number z equal to 1 positive I in algebraic or in standard form. This complex number is the same as square root of 2 as radius in factor of cosine of pi out of 4, positive I sine of pi out of 4. Then the polar form of this complex number is this one. Then I say, give me flowers, and my lesson is ended. Let us give you exercise to deal with. Exercise, where is the duster? Exercise. Find the polar form. Find the polar form. When I say polar form, the same as a trigonometric form. Find the polar form of the following. The polar form of the following complex numbers. Find the polar form of the following complex numbers. Number A, z equal -1 positive I. Number B, Z equal 1 negative I. Number C, Z equal negative 1 negative I. Number D, Z equal 2I. Then deal with this exercise teachers for a kind of improving your knowledge. I say bye bye.